Hi guys. Today's lesson is 2.10 on field theory and universal gravitation. So field theory talks about these invisible gravitational fields that surround all objects at all times. So every mass in our universe creates its own gravitational field. So the big thing we think about is planets creating a gravitational field, but anything that has mass also has a gravitational field. So you sitting watching this video right now have a gravitational field yourself. It just happens to be much smaller than the planet that you're sitting on. So these lines that we draw are still vectors and they point towards the center of the mass, so Earth or other planetary bodies. And the closer they are together, the stronger the gravitational field. So if we look at this picture here, we have the moon and the Earth. And you can see if you look closely that all of these lines are vectors. They have arrowheads pointing towards the center of the mass. And obviously, we can see from how close the lines are on Earth's gravitational field that that would be much stronger than the gravitational field of the moon, where the lines are much more spaced apart. So that means that the Earth is going to have a stronger gravitational field because it has much more mass than the moon. These field lines can be added together just like vectors. So here's the simplified version of the Earth and the moon. So we've just taken one vector arrow from the Earth and one from the moon in the same direction to simplify this down. And what's happening is you have the Earth, and then I'm just going to draw this arrow here, tip to tail, because it is a vector arrow with Earth. So this little one is the gravitational field that the moon is exerting on Earth. So that little bit is going to cancel out, and your resultant is going to be here. What does this resultant show you? Well, this shows you exactly why the moon is orbiting the Earth and not the other way around. Because the resultant gravitational field after those have canceled is pointing towards the center of the Earth. The Earth is pulling the moon closer to it all the time, and therefore it orbits around the Earth. So we know the direction field lines can move in. So now we need to figure out the magnitude. So we need to use some equations, do some math to figure out the numbers here. Here's Newton's second law. Force equals mass times acceleration, adjusted for the force of gravity, being mass times acceleration due to gravity. But we're actually going to introduce different units for acceleration due to gravity, and we're going to call it something different. So let's think about force in newtons. Mass is in kilograms. And I'm going to isolate for G. So I want to figure out what are the units on this different G that's really the same G, but I'm just going to use slightly different units. I'm going to divide both sides by kilograms. And I've got this G to be newtons over kilograms. It really is meters per second squared. If I wrote newtons with the fundamental units that it's made out of, they would all cancel out and leave us with meters per second squared. So newtons per kilogram are meters per second, but newtons per kilogram just tell us that we're talking about the strength of the gravitational field instead of acceleration due to gravity, like we have been in the first unit. Now, Fg is still the force of gravity on some object, and m is still the mass of the object. We're just talking about different units and a different way of thinking about G. So G means for every Newton of force, we're looking at how much that applies per 1 kilogram of something. That's what this new G is saying. So you can see here's the second page of the formula sheet at the bottom where you find all of your constants. We have given you A and G as 9.81 and negative 9.81, and we have given you the two different units. So just thinking about acceleration due to gravity in a different way as gravitational field strength. If we release a test object in a gravitational field, it will accelerate in the direction of the field with a force proportional to the mass of the object. So if I dropped something right now, it would accelerate in the direction of the gravitational field with a force proportional to the mass of the object. So if I dropped, let's say, a bowling ball on Earth, it would accelerate towards the center of Earth, and it would be proportional to the mass. The force would be proportional to the mass of the object. So there's going to be a bigger force gravity for a bowling ball than there would be for, say, a tennis ball. Now, this is different than the speed that it would go and the acceleration it would go. This is the force that's going to be proportional to the mass. We can see this if we take a bowling ball or tennis ball to the moon and we drop them there. The force that they're going to drop is much smaller because the mass of the moon is much smaller. So in this example, there's an object that has a mass of 175 kilograms. It's experiencing a force of 480 newtons toward the Earth, so that's force gravity. What is the strength of the field at that object? So this is saying strength of the field. This is saying gravitational field strength, which is on your formula sheet. It's G. That's what we're looking for. So here's my formula. I'm going to rearrange for G, which is what I want, by dividing both sides by mass. I'm going to sub my force and my mass in there. So my force was 1480 newtons, and my mass was 175 kilograms. And I'm getting the gravitational field strength of this object to be 8.46 newtons per kilogram. And this is going to be towards the center of Earth. A test object of mass m experiences a field strength of G. If the mass doubles and the force acting on the object stays the same, what must happen to the field strength? This is a really important concept for moving forward in Physics 30. You can see that we aren't working with numbers. We're not telling you what the mass of this object is. We aren't telling you the gravitational field strength, so we don't know if it's on Earth or the moon or some other planet. We just know that the mass is doubling and the force is staying the same. So we have to do some work within the formula with these few numbers that we have. So we're going to write the formula down. Okay. We're going to do what the formula is saying here. It's saying if the mass doubles and the force stays the same. So we need to keep the force of gravity the same number, but we're going to double the mass. I can't just put a 2 inside of an equation and have it still remain equal on one side and the other. I need to do something to counteract the 2. So what kind of number could I multiply by on this side here so that I could cancel the 2? 1/2 will cancel the 2. The other way you can think about that is I multiplied by 2 for the mass. So if I divide by 2, it's like I've done nothing at all. Take the number 10, multiply it by 2, now cut it in half. You should be right back at 10. So these two numbers in blue have just canceled each other out. So that means that if I double the mass, and remember that this force of gravity has to stay the same. If I double the mass and then I take g and I cut it in half, I'm going to get force gravity staying the same. So let's put this into words. What has to happen is that the g, aka the field strength, has to be half as big. And in English, you can say that a number of different ways. You can say that it halves, you can say that it divides by 2, cuts in half, whatever. Now, on this next page, we talk about these proportionalities. So we see that we've got G is proportionate to M. We also know from something in the textbook that G is proportionate to 1 over R squared. You don't need to know how we arrived at that, but the page in the textbook is referenced if you're interested, but don't worry about figuring that out. If we combine these two proportions together, so that's all that this little symbol means is proportions, we actually come up with the next formula on your formula sheet. So little g equals big G times m divided by r squared. So let's talk about what all of these parts mean. We've got little g, which before today would have been meters per second squared. But I'd like you to cross that off and do newtons per kilogram because it's gravitational field strength. Big G is the universal gravitational constant. It's the same everywhere in the universe. It's a constant number that's on your formula sheet. So big G is on the bottom of the second page, 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. It sounds like a handful, but it's actually pretty easy to work with as long as you know scientific notation. So there's that one. There's M, so mass of gravity producing object. So you'll have to decide what is producing the gravity in your question. And then the distance between test object and gravity producing object. Okay. Now distance is measured in meters. Mass is measured in kilograms. And universal gravitational constant, Newton meters squared per kilogram squared, I believe. Yes. So big G, the constant of proportionality, there it is. It's on your formula sheet. It's the same everywhere in the universe. Since it's a constant, kind of like 9.81, it's not something that factors into your sig digs. The value is calculated through something called the Cavendish experiment. And I've got a really good YouTube video linked here where a student sets up the Cavendish experiment and discovers what big G is just in her bedroom, actually using some pretty basic science equipment. So please watch that video when you're done with this lesson, and you'll see how big G was kind of discovered. Let's use that now to calculate the gravitational field strength. So gravitational field strength, meaning little g, on the surface of the Earth. So one thing that's tricky about these questions is there's no numbers up there. They've said find little g on the surface of the Earth, not a single number said. But if you look on your formula sheet, you have a lot of information about the Earth. You have the Earth's mass and you have the Earth's equatorial radius. So that's the radius at the equator. Okay. We can use these numbers in this question because we need, for our formula, mass and radius. So we're going to use those exact two numbers. Here's the formula that we just created from proportionalities. So we'll sub in. This section is really a test of your calculator work with scientific notation more than anything. 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared, and you're just copying that off the formula sheet. The mass of the Earth, again from the formula sheet, is 5.97 times 10 to the 24 kilograms. And on the bottom, remember that this is r squared. So put your bracket and put the squared outside. It's very important that the squared's outside. And we're going to put the radius of Earth, 6.37 times 10 to the 6 meters. And now you need to make sure that you can enter this in your calculator. So pause the video, put the brackets exactly where we've put them, put the squared in the right place, and see if you can calculate a number that makes sense. It should not be a surprise that you get 9.81 newtons per kilogram. This is a number that we've just kind of blindly been subbing into formulas all semester as acceleration due to gravity. So gravitational field strength on Earth should be 9.81 newtons per kilogram. Calculate the gravitational field strength on the highest peak of Everest. So this is where it's actually 8,848 meters above the Earth, so above sea level. So what we need to do here is we need to take the number off the formula sheet, so the equatorial radius, the average radius of Earth, and we need to add the 8848 to it. So it's the same equation, gm over r squared. Put in your g. It's a lot of writing, but it's not really complicated math once you learn your calculator. And then on the bottom here, we have to take our radius of Earth that we used in the previous question, and we have to add the 8848 before we square it. So it's very important that that addition happens before squaring. We need to make sure that we follow BEDMAS for this, and those brackets are absolutely essential. Pause the video and put this in. And what you should get is 9.79 newtons per kilogram. So think to yourself, does it make sense that we've got a smaller acceleration due to gravity when we're on the top of Mount Everest? So we're further away from the mass that's causing the gravitational field. So we would have less acceleration due to gravity or gravitational field strength. So the further you get away, the less that object is acting on you, the less the gravitational field strength is. You would think by similar logic that if you got closer to that object, that the gravitational field strength would then increase. So see if that's true for the next example. Try pausing the video and doing the next one where we're actually at the lowest point on Earth, which is the bottom of the Marianas Trench, which is 11,034 meters below the surface of the Earth. This calculation is essentially exactly the same as above, but instead of adding the extra distance away from the sea level that you are, you're actually going to minus it. So all of the numbers on the top are the same. It's a lot of writing with your pencil, but you'll get quick at it. And the bottom is now a subtraction. Before you square, again, making sure that you're really cognizant of bed mass rules here. So you should get a number that makes sense to you. We just said that the gravitational field strength, the closer you are to the center of the mass, should be stronger. So we're thinking it should be stronger than 9.81, which the numbers end up being 9.85 newtons per kilogram, verifying what we thought to be true. Calculate the gravitational field strength on a planet whose mass is 1/8 of that on Earth and whose radius is 3 times larger. So we're writing the same numbers for Earth, but we're going to take the mass and we're going to do 1/8, which is just dividing by 8, and we're going to take the radius and triple it. So it's going to look like this. Nothing tricky going on with G. It's still just 6.67 times 10 to the negative 11. But for the mass of Earth, 5.97 times 10 to the 24, they've told us that the mass of the planet that we're talking about is actually an eighth, so divided by 8 of Earth's mass. Okay, so if you had something that was 80 kilograms and I said, this thing I'm holding is an eighth the size, you would say, okay, 80 divided by 8, the thing you're holding is 10 kilograms. This is exactly what we're doing, just with more complicated looking numbers that include scientific notation. Now we want to triple the radius so that it's 3 times larger. So the radius of Earth being that 6.37 times 10 to the 6 number. And we want to times that by 3. Now think about your bed mass. The radius of the planet we're talking about needs to be squared. This whole square bracket is the radius of the planet we're talking about. It's 3 times Earth's radius. That number needs to be squared. So you absolutely need to have kind of those double brackets happening so that you multiply by 3 before you square. Make sure that you can put this in your calculator and get 0.136 newtons per kilogram. So we don't even know the planet's name, but we just know that it's an eighth of the mass of Earth and 3 times larger for radius. And we can figure out the acceleration due to gravity, or in this section, the gravitational field strength. Here's the next formula in your formula sheet. It's called Newton's law of universal gravitation. So he not only worked out a formula for field strength like we just worked with, but he also combined this with his second law, F equals ma, to determine the law of universal gravitation. So this one is Fg equals big G times 2 masses divided by r squared. So what this is talking about is the force of gravity between two objects. So you could figure out the force of gravity between yourself and the planet Earth because you have mass, Earth has mass, and you are a certain distance apart, which is the r squared on the bottom. So force of gravity, we always measure that in newtons. G on your formula sheet, kind of, the ugliest units you've ever seen in your life, but there they are. Mass, both of these measured in kilograms. And distance between, now highlight this, the centers of the objects. This becomes really important when we're talking about planets because you have to factor in the radius of the planet in order to get to the center. So this will be measured in meters. What is the force of gravity between two neutrons placed 150 picometers apart? Now, picometers, you'll work with all sorts of different prefixes in physics 30. And I would, in physics 20, just give you what this size is. A picometer is 10 to the negative 12. So this number is 150 times 10 to the negative 12 meters. Okay, that's what we're going to use for our R. Neutrons, on the physics 30 formula sheet, I know you don't have that, but on the physics 31, we would actually give you the mass of a neutron to be 1.67 times 10 to the negative 27 kilograms. And we're looking for force of gravity, so you need to know your terminology. The last formula, little g, was finding gravitational field strength. Force of gravity is Fg. So you need to know when you're on your formula sheet and you're deciding between, in the dynamic section, Fg equals gm1 m2 over r squared, and little g equals gm over r squared. You have to decide which one you're using based on the terminology in the question. Are you looking for force gravity or gravitational field strength? Very different things. We're looking for Fg, gm1 m2 over r squared is our formula. Big G is always the same. It's on your formula sheet. It's a constant, and it does not factor into sig digs. Mass 1 and mass 2. Well, we're working with two neutrons, so both of them are 1.67 times 10 to the negative 27 kilograms. So I could write that twice, but when you're writing so many scientific notation numbers, and they're so long to write, it's really helpful if there's a shortcut. Can you think of a shortcut instead of me writing this number an entire another time to multiply? That's the same as squaring. It doesn't work for every question. It only works because the masses are exactly the same. It's two neutrons, which weigh the same amount. So in this case, I can just square the 1.67 times 10 to the negative 27. Here's my 150 picometers on the bottom, and squared. Pause the video, enter it in your calculator, and make sure you can get my answer. All right, so after putting everything in my calculator, I come up with a force gravity of 8.27 times 10 to the negative 45. And since it's a force, all forces are measured in newtons. If the distance between two objects doubles and the mass stays the same, what can be said of the force of gravity between them? It can be handy to do this in different colors or with highlighters if you have them. We're working with this formula. And we're going to do some doubling, staying the same, and determine what happens to the force gravity. So what I'm going to do is I'm going to take the distance and double it. So that's r. R is going to double before it gets squared. That's very important. And the mass of the objects is staying the same. Obviously, big G, the universal constant, it's the same everywhere in the universe. It's not going to be able to change. It's universal. So what would happen here to Fg? Well, think about this too. The brackets are important because the 2 gets squared. 2 squared is 4, and that's multiplying by the original radius squared that would have been in the equation. The top stayed the same, and I could put a secret 1 on the top if it helps us to see what's happening. Let's bring this number out in front. It's really the number 1/4 times the original formula for Fg. So by doubling the distance between the objects, it actually makes this which is Fg, 1/4 as big. So we could say this as force gravity is reduced by 1/4 when distance between is doubled. I know this is kind of abstract that we're not putting numbers into our calculator. We're just putting numbers into the equation, pulling them out in front, and saying in words what happens to the force of gravity. So try that for the next one. Now you're going to take the distance between two objects, r, and you're going to half that. You're going to cut it in half. You're going to take the mass of one object and leave it, and you're going to triple the mass of the other. It doesn't matter which one stays the same and which one triples. Then you're going to pull all the numbers that you inputted into the equation out in front and make a final statement about what happened to force gravity. Here's the solution. Force gravity is G m1 m2 over r squared. I'm going to do distance between the objects cut in half. I'm going to leave m1 the same, and I'm going to triple m2. I'm going to pull all of my numbers out of the equation now. This 3, I'm going to pull in front. This 1/2, I'm going to square to get 1/4, and I'm going to pull it in front. And what remains is all of the stuff that was originally in the question, which is the same as Fg. So this number here, there's a much nicer way to say this number, and I prefer when students work through it in their head, but of course you can put it in your calculator. We should all be able to work with fractions like this. What is 3 divided by 1/4? Well, division of fractions turns into multiplication of the reciprocal, and then you're going to go top times top, bottom times bottom, and you're going to get the number 12. So Fg has actually multiplied by 12. If you take the distance between two objects and cut it in half, and you make the mass of one object 3 times bigger while the other object has the same mass, the force of gravity is going to be 12 times bigger. So here's the assignment for this lesson. Read page 203 to 214. Now, you can read about the torsion balance, but this is going to be addressed when you watch the video that I'm sending with this lesson about the girl doing the Cavendish experiment in her bedroom. You can read about tides. It's more just useful, interesting information that helps you to think about the force of gravity and gravitational field strength. It helps explain some things when we think about the moon and the force of gravity and tides. And then gravity assist. If you have time, I really recommend watching the movie Apollo 13. In my past experience, I found out that students usually haven't seen this movie. It's a true story. It's quite an amazing story. And they use gravity assist to slingshot the space shuttle around the moon and send it back towards Earth. It's really quite incredible. So if you can watch Apollo 13, even make it a nice family movie night, that would be great. It explains a lot of physics that we actually can understand after this lesson. There's also 6 questions on page 215 to do after all of these videos are watched. It'll make it a lot easier. I love to answer your questions. Please email me, and I'd love to hear from you if you're having any trouble at all. I know there's a lot more math, a lot more calculator work going on, so I'd love to help walk you through it.